the storm did not announce itself. That is the first thing to understand about it, because the way a storm arrives in a meteorologist's awareness shapes everything about how it is subsequently understood and communicated. Some storms announce themselves through the models, showing up as organized systems in the ensemble guidance days before any organized convection has appeared in the satellite imagery, allowing forecasters the luxury of watching the projected development and preparing their communications in advance. Some storms announce themselves through the observations, a small area of disturbed weather that the satellites begin tracking and that gradually reveals itself, over days of monitoring, as a system with a structural organization and the environmental support to become something significant. And some storms announce themselves through the data, specific measurements from specific instruments that do not fit the expected pattern, and that, when examined carefully, turn out to be the early signature of something that the standard monitoring had not yet recognized. This storm announced itself through the data. The meteorologist, who was processing the buoy observations from the Central Pacific, noticed it first, though noticed is perhaps too active a word for what happened. The buoy data was displaying on his screen in the standard format, rows of numbers representing wind speed and wind direction and sea level pressure and sea surface temperature at dozens of locations distributed across the Pacific. And he was working through the quality control checks that are the routine morning task of the shift, flagging suspicious values for review and confirming that the values that looked correct were consistent with the broader synoptic picture. The pressure reading at one specific buoy caught his attention, not because it was dramatically anomalous, but because it was slightly low relative to the surrounding buoys, a gradient that implied a weak cyclonic circulation in the vicinity that the standard morning analysis had not highlighted. He noted it in the log and moved on. Then, in the routine completion of the quality control, he found a second buoy 40 kilometers away, showing a similar pattern, and a third buoy 60 kilometers in a different direction, showing the same thing. 3 buoys, each individually unremarkable, together describing the edge of a pressure gradient that was inconsistent with the morning analysis. He pulled up the most recent satellite imagery. The morning visible imagery showed nothing organized. The infrared showed a broad area of high cloud that could be associated with any number of features in the tropical atmosphere. The microwave imagery, which can penetrate the high cloud layer and reveal the precipitation structure beneath, showed, in the specific location implied by the buoy pressure anomalies, a small but organized region of deep convection with a spiral geometry that was not quite the loose, disorganized scatter of random tropical convection, and was not yet the clearly defined spiral bands of an established tropical system. It was something in between, in the specific transitional state that experienced forecasters call the system is trying to get organized, the phase where the outcome is genuinely uncertain, and where the decisions made about monitoring and communication in the next 24 to 48 hours will shape how well prepared anyone is for what comes next. He escalated the observation to the lead forecaster and went back to his quality control. The lead forecaster looked at the buoy data and the satellite imagery for approximately 6 minutes. Then she picked up the phone and called the Regional Meteorological Center in Tokyo. After a brief conversation that included the sharing of the specific buoy locations and the satellite imagery timestamp, she wrote a note in the forecast discussion that went into the morning operational package. The note was 2 sentences long. The second sentence read, "The system merits increased monitoring frequency and a formal development assessment within 12 hours. By the end of that day, the meteorological community that monitors the Western Pacific had its attention on a disturbance that most of them had not known about that morning." By the end of the following day, the word watching had become the correct verb for what they were doing. In the specific meteorological sense of watching that implies focused attention, continuous data review, and the accumulation of evidence that will eventually support either concern or reassurance, but that in the interval supports only the patient and disciplined observation of a system that has not yet decided what it is going to be. There is a specific kind of professional tension that meteorologists develop when they are watching a storm closely, and it is a tension that comes from the simultaneous demands of 2 obligations that do not always point in the same direction. The first obligation is to communicate current threats accurately and completely, to ensure that the communities that might be affected by a significant storm have the information they need to make good preparedness decisions. The second obligation is to communicate accurately in the scientific sense, to represent the genuine uncertainty in the forecast, and to avoid overstating the confidence in specific outcomes that the data does not yet support. When a storm is well developed, and its track and intensity are relatively certain, these 2 obligations are relatively easy to reconcile. When a storm is in the early stages of organization, when the question of whether it will become a significant threat is genuinely open, the 2 obligations pull against each other in ways that require careful professional judgment to navigate. The system that the buoy anomalies revealed is precisely the kind of storm that makes this tension acute. The environmental conditions in which it is developing are, by most of the standard metrics that forecasters use to assess whether a developing disturbance has the support it needs to become a significant tropical cyclone, favorable to a degree that is at the upper end of what the climatological record shows for similar calendar periods. The sea surface temperatures in the development region are elevated above the 30 degrees Celsius threshold that is widely regarded as the minimum for rapid intensification, and they are elevated by enough margin that the thermodynamic potential for deep convection is high. The wind shear in the development region, the change in wind speed and direction with altitude, that is one of the most important limiting factors for tropical cyclone development because high shear disrupts the organized warm core structure, is low, within the range that has historically been associated with rapid intensification in the Western Pacific. The moisture content of the atmosphere in the development region is high, consistent with a saturated tropical environment where the thermodynamic inhibition to deep convection is minimal. Against these favorable factors, the current system has several characteristics that are less favorable. The circulation is not yet well defined at the surface. The deep convection is organized but not symmetric in the way that well-developed tropical cyclones are. The upper-level outflow, which needs to be well established and efficient for a tropical cyclone to sustain intensification, is present but patchy rather than the continuous and expansive pattern that characterizes rapidly deepening systems. These deficiencies are consistent with a system that is in the early stages of organization, and that has not yet established the internal dynamics that allow tropical cyclones to sustain themselves and intensify efficiently. They could resolve over the next 24 to 48 hours if the environmental conditions remain favorable, and if the system's internal organization continues to develop, producing a storm with the full suite of characteristics of a developing tropical cyclone. Or they could persist or worsen if some aspect of the environmental support degrades or if the organizational development is disrupted before it reaches the self-sustaining threshold. This is the genuinely uncertain state that the meteorological community is watching, and the watching is intense precisely because the consequences of the two possible outcomes are so different. A system that organizes into a significant tropical cyclone over a region of the Pacific, where the large-scale flow is favorable for specific tracks toward populated coastlines, could produce a threat that requires substantial preparedness action by communities that currently have no warning. A system that fails to organize, that dissipates or remains a weak, disorganized disturbance, requires no community preparedness action and produces no harm. The gap between these two outcomes is wide, and the gap between the current state of the evidence and the state of evidence that would allow the two outcomes to be confidently distinguished is what the close watching is trying to close. The meteorological watching of a potentially developing storm involves multiple layers of observation that operate simultaneously and that each contribute different kinds of information to the collective picture that the forecasters are assembling. The geostationary satellite imagery, which provides a nearly continuous visual record of the cloud structure over the storm region, updated every few minutes, is the most widely available and most immediately interpretable layer. Forecasters and researchers who work with tropical meteorology develop an expert ability to interpret the character of the cloud organization visible in the satellite imagery, reading the architecture of the deep convection and the cirrus outflow in the low-level cloud bands for the signs of a system that is organizing and deepening versus one that is struggling or disorganized. The current system in the satellite imagery is showing what experienced forecasters describe as episodic pulses of deep convection, periods during which a burst of organized convection develops around the circulation center and then decays, followed by a period of weaker convective activity and then another burst. This pulsing pattern is common in systems that are trying to organize and that have not yet established the steady-state convective organization of a well-developed tropical cyclone, and its presence is consistent with a system in transition rather than a system that has already determined its trajectory. The microwave satellite imagery, which as noted earlier can penetrate the high cloud layer and reveal the precipitation structure at lower levels, is providing a more precise picture of the developing circulation than the visible imagery alone. The microwave imagery shows the location and the intensity of the deep convective towers that are the thermodynamic engine of the developing system. And the pattern of those towers relative to the circulation center is one of the most useful indicators of whether the system is organizing efficiently. A developing tropical cyclone that is organizing well tends to show deep convection that is concentrated around the circulation center in a way that wraps progressively closer to the center over time, a process that meteorologists call the convective wrapping of the center that is associated with the intensification of the near-center winds and the development of the characteristic circular structure of a mature tropical cyclone. The current system is showing this process in early stages, with the deep convection gradually becoming more concentrated around the center across successive microwave satellite passes. The ocean surface wind field, measured by the scatterometer instruments aboard several satellites that pass over the development region at intervals of 12 hours, is providing the most direct measurement of the low-level circulation that the satellite observation system can currently provide. The scatterometer data shows wind speed and direction at the ocean surface across a swath of several hundred kilometers, and the pattern of surface winds around the developing system is one of the key indicators of the strength and organization of the low-level circulation. The current scatterometer passes are showing a cyclonic circulation in the development region with maximum surface wind speeds that are in the range of 20 to 30 knots, below the tropical storm threshold of 34 knots, but above the background level of the trade wind environment. The cyclonic signature is becoming more organized and more symmetric across successive scatterometer passes, which is consistent with the overall trend toward organizational development that the other satellite observations are showing. The dropsonde aircraft, which fly reconnaissance missions through and around tropical systems to obtain the in situ wind and temperature measurements that are essential for accurate analysis of storm structure, have been requested for the development region. The reconnaissance aircraft from the aircraft reconnaissance networks of the United States and Japan have been scheduled for the region, and the data from the first reconnaissance missions should be available within the next 12 hours. The dropsonde data will provide the most direct and accurate measurement of the system's circulation structure, thermodynamic characteristics, and intensity that is currently available, and its arrival in the data assimilation systems of the operational models will significantly improve the model's representation of the current state of the system and their ability to project its future evolution. The specific meteorologists who are watching the storm most closely are concentrated at a small number of institutions and operational centers that have the responsibility and the resources to provide the intensive monitoring that a potentially developing tropical cyclone warrants. The Joint Typhoon Warning Center, the central node of the United States military's tropical cyclone monitoring capability for the Pacific and Indian Oceans, has been tracking the disturbance since the morning of the buoy anomaly report and has been producing the development assessments and intensity forecasts that are the primary products of its operational function. The Japan Meteorological Agency, whose regional responsibility covers the Western Pacific and whose operational forecast products are the primary warning guidance for Japan's coastal communities, has been running its typhoon ensemble prediction system for the development region since the system was formally identified as a tropical disturbance. The Regional Specialized Meteorological Center for Tropical Cyclones in the Western Pacific Basin, operated by the Japan Meteorological Agency, has been coordinating the formal international response to the developing system, and will issue the advisories that trigger formal watches and warnings when the observational evidence supports them. Each of these centers has meteorologists who have spent careers studying tropical cyclone development in the Western Pacific, who have watched dozens of systems through the early organizational phase that the current system is in, and who have developed the pattern recognition expertise that allows them to read the satellite imagery and the model guidance and the observational data with the specific knowledge of what is significant and what is noise. Their individual assessments of the current situation are being compared and discussed through the formal and informal coordination channels that the WMO framework supports, and that the operational meteorological community has built over decades of collaboration. The consensus that is emerging from these discussions is not a confident prediction of what the storm will do. It is a probabilistic assessment of the range of outcomes that the current evidence supports, weighted by the confidence that the meteorologists place in different aspects of the evidence, and shaped by their knowledge of how similar situations have evolved in the historical record. The consensus is that the probability of tropical storm development within the next 48 hours is substantially elevated above the climatological base rate for disturbances with similar characteristics in this region at this time of year. That the environmental conditions are supportive of further intensification if tropical storm development occurs, and that the track, if the system develops, would bring it toward a sector of the Western Pacific, where populated coastlines are within the range of potential impacts. This is not a forecast of a specific intensity and a specific track. It is a probabilistic framing of the situation that the meteorologists find most honest given the current state of the evidence, and it is the kind of framing that requires the emergency management community that receives it to make decisions under uncertainty, to allocate preparedness resources and public communication efforts in a way that is proportionate to the probability and magnitude of the potential threat without being driven by a single deterministic projection that may prove incorrect. The history of tropical cyclone forecasting is in significant part a history of the decisions made in the early organizational phase of developing storms, when the evidence was ambiguous and the forecasters had to choose between communicating the potential threat early and risking the credibility cost of an eventual non-event, and waiting for the evidence to become clearer and risking the human cost of late or inadequate warning. The history contains both kinds of errors, cases where warnings were issued for storms that did not materialize, and cases where storms that were clearly going to be significant were not adequately communicated until too late for effective preparation. The learning from both kinds of errors has shaped the current operational protocols and the communication frameworks that the meteorological community uses, and the accumulated learning is visible in the current response to the developing system. One of the most important lessons from the history of tropical cyclone warning is the asymmetry and the consequences of the two types of error. A false alarm, a warning for a storm that does not materialize, has costs in the economic disruption of evacuations and business closures, in the erosion of public trust that makes future warnings less effective, and in the financial and operational burden on the emergency management agencies that mobilize resources in response to the warning. These costs are real and they matter, but a missed warning, the failure to adequately communicate a threat that does materialize, has costs that are of a fundamentally different character. The missed warning costs are measured in human casualties and in the permanent harm to the individuals who were not given the information they needed to protect themselves. These costs are irreversible in a way that the costs of a false alarm are not. The operational protocols that govern tropical cyclone warning today reflect a deliberate weighting that prioritizes avoiding missed warnings over avoiding false alarms, on the grounds that the irreversible human costs of the former are more serious than the recoverable costs of the latter. This weighting is not absolute, because the credibility cost of false alarms can, if the false alarm rate is high enough, make all warnings less effective by training the public not to respond to them. In a warning system whose effectiveness has been degraded by credibility, erosion produces its own missed warning consequences. But within the range of reasonable error rates, the protocols are calibrated to err on the side of early warning and broader warning areas rather than on the side of waiting for certainty that operational forecast lead times can never fully provide. The current situation is being managed within this framework, with the meteorological agencies issuing the development assessments and the elevated monitoring products that communicate the potential threat without making the specific intensity and track claims that the evidence does not yet support. The communities in the potential impact region are being given the information that something is developing, that the probability of a significant threat is elevated, and that they should be monitoring the official products for updates that will provide more specific guidance as the situation evolves. This information, properly communicated and properly received, supports the kind of proportionate preparedness response that the asymmetric consequence calculus of tropical cyclone warnings recommends. The communities that are in the potential impact region of the developing storm are distributed across a broad arc of the Western Pacific, encompassing coastal areas of the Philippines, Taiwan, Japan, and the Ryukyu Islands, each of which has a different level of typhoon preparedness infrastructure and a different history of typhoon experience that shapes how the population responds to early warning information. The Philippines, with its long history of typhoon landfalls and its extensive national preparedness infrastructure, has local and national emergency management agencies that are already in communication with the Joint Typhoon Warning Center and the Philippine Atmospheric, Geophysical, and Astronomical Services Administration about the developing system. The national and local government units in the potential impact provinces have begun the early preparedness activities that the Philippine Disaster Risk Reduction and Management Act requires when a tropical cyclone development assessment identifies a potential threat, reviewing the status of evacuation centers, confirming the readiness of the early warning communication systems, and ensuring that the public is aware that a potentially significant tropical system is being monitored. Taiwan's Central Weather Administration is tracking the system, with a specific focus on the track scenarios that would bring a developing typhoon toward the island, which sits in the Western Pacific, in a geographic position that makes it one of the most frequently typhoon-impacted landmasses in the basin. Taiwan's typhoon preparedness infrastructure is sophisticated and well-practiced, reflecting decades of typhoon experience and sustained investment in both the physical and institutional dimensions of preparedness. The Central Weather Administration's ensemble forecast system is being run specifically for the developing system, providing the probabilistic track and intensity guidance that supports the graduated alert system through which Taiwan communicates typhoon threats to its population and coordinates the preparedness response of its emergency management agencies. Japan's preparedness response to the developing system is coordinated through the Japan Meteorological Agency's Typhoon Information Center and through the formal coordination mechanisms between the JMA and the prefectural governments of the regions potentially at risk. Japan's typhoon preparedness culture is among the most deeply embedded in any typhoon-affected society, shaped by the long history of significant typhoon landfalls and by the national investment in both physical typhoon protection infrastructure and public preparedness education. The JMA's communication of the current situation to the public is being calibrated to provide the early awareness that the potential threat warrants, without triggering the specific actions that are reserved for more imminent threats, using the probability language that the JMA has developed over years of public communication about typhoon uncertainty. The scientific community that studies tropical cyclone development and intensity is engaged with the current situation through multiple channels that operate in parallel with the operational meteorological communities watching. Several research groups that specialize in tropical cyclone genesis, the processes by which tropical disturbances develop into tropical cyclones, have been examining the current system as a potential research case that will contribute to their understanding of how tropical cyclone development occurs in the specific oceanic and atmospheric conditions of the current period. The Genesis research community has been working on the problem of what determines which tropical disturbances develop into tropical cyclones and which do not, a problem that is fundamental to tropical cyclone prediction, and that has been resistant to complete solution despite decades of intensive research. The statistics are striking in their implications. Of the approximately 100 tropical disturbances that form each year in the Western Pacific Basin and that receive development assessments from the operational centers, only a fraction develop into named tropical storms, and an even smaller fraction become typhoons. The factors that determine development versus non-development are a combination of the environmental conditions, the thermodynamic and dynamic characteristics of the atmosphere and ocean in the development region, and the internal dynamics of the disturbance itself, the specific structure and organization of the developing circulation and convection. Both sets of factors contribute to the outcome, but their relative importance and the specific thresholds that matter have been difficult to establish with the precision needed to significantly improve Genesis forecasts. The current system is developing in conditions that are at the favorable end of the Genesis parameter space, which means that the external environmental conditions are not the factor that will determine whether development occurs. If the system fails to develop, the failure will be attributed primarily to the internal dynamics, to some aspect of the developing circulation structure that does not achieve the self-sustaining organization required for tropical cyclone genesis. The research community is therefore watching the current case with specific interest in the internal dynamics, in the way the convection is organized relative to the circulation center, and in the evolution of the warm core structure that is the defining thermodynamic feature of a tropical cyclone, as potential evidence for the specific internal dynamical factors that differentiate development from non-development in favorable environments. The results of this real-time research observation are contributing to the operational forecast discussions through the informal connections between the research and operational communities that are one of the most productive features of the current structure of meteorological science. Researchers who are examining the satellite imagery and the model output for their scientific interest are sharing their observations with operational forecasters who are making the formal forecast products, and the operational forecasters are asking questions about specific features of the developing system that the researchers' expertise can help interpret. This real-time collaboration is not formalized, but it is genuine and productive, and it is one of the ways in which the improvement of tropical cyclone forecasting is continuously driven forward, even between the major research programs and modeling upgrades that represent the more visible investment in forecasting improvement. The question that is most important for the communities potentially affected by the developing storm, and that the meteorological watching is working to answer as rapidly as the evidence allows, is not simply whether the storm will develop, but what it will do if it does. The track and the intensity of a developed tropical cyclone are the parameters that determine the specific geographic distribution of the hazard and the level of that hazard. And they are the parameters that the warning system needs to communicate with sufficient precision and sufficient certainty to allow communities to make the preparedness decisions that will determine the human outcomes. The track forecast for a tropical cyclone that has not yet fully developed is fundamentally limited by the fact that the storm does not yet have the coherent structure that the track forecast methods depend on. Track forecasting for established tropical cyclones relies on the analysis of the large-scale environmental flow in which the storm is embedded, the steering current that carries the storm along a trajectory determined by the large-scale atmospheric circulation, supplemented by the beta drift effect that causes tropical cyclones to deviate from the pure steering current direction due to their interaction with the Earth's rotation. Both of these processes require a well-defined circulation center with a definite vertical structure, which the current developing system does not yet have in its underdeveloped state. The track guidance that the operational models are producing for the current system has a spread that reflects both the uncertainty in the system's future track and the uncertainty in its development, the range of tracks that developing tropical cyclones in this region and this environmental flow would follow, combined with the uncertainty about whether a developed tropical cyclone with a trackable center will actually emerge from the current disturbance. This combined uncertainty produces wide probabilistic track envelopes that are operationally useful in the sense that they define the region that potentially affected communities should be tracking the official advisories for, but that are less useful in the specific sense of identifying which specific communities should be taking the most urgent preparedness actions. The narrowing of the track uncertainty as the system develops and as its center becomes better defined by the observations is one of the key near-term developments that the meteorological community is waiting for. Each successive reconnaissance aircraft mission into the developing system will produce better measurements of the center position and the circulation structure. And each improvement in the position analysis will improve the model initialization and thereby improve the track forecast. The improvement is progressive, and the track uncertainty will remain elevated until the system has developed to the point where the center is well defined and the model analyses are accurately representing its position and structure. The intensity forecast has its own set of challenges that are related to but distinct from the track forecast challenges. Even for well-developed tropical cyclones with well-analyzed centers and accurate model representations, intensity forecasting is the component of tropical cyclone prediction with the lowest skill and the most significant remaining gap from a practical standpoint. The rapid intensification events that produce the most catastrophic tropical cyclone impacts, the overnight doublings of wind speed that can take a moderate typhoon and turn it into a super typhoon before the coastal communities in its path have had time to respond to the revised threat level, or the aspect of intensity forecasting that continues to challenge both the operational forecasters and the research community in ways that have not been resolved despite decades of focused research effort. The current developing system is in a region and an environmental state that the research community has identified as favorable for rapid intensification if and when the system reaches tropical storm strength. The same characteristics that make the environment favorable for tropical cyclone development also make it favorable for rapid intensification. The elevated sea surface temperatures, the deep warm layer in the ocean, the low wind shear. The specific intensity trajectory of the current system, if it develops, will depend on these environmental factors and on the internal dynamics of the developing storm. And the combination of favorable conditions is producing model guidance that includes a significant probability of rapid intensification occurring in the 24 to 48 hours after initial tropical storm formation. The implication of this guidance for the communities potentially in the storm's path is that the storm they need to prepare for may be significantly stronger at the time it would affect them than it is at the time the first formal watches and warnings are issued, because the rapid intensification could occur during the period between the issuance of the initial watches and the arrival of the storm at the coast. This rapid intensification problem, the possibility that the storm that arrives is much stronger than the storm that was forecast when the community's preparedness decisions were made, is one of the most challenging aspects of tropical cyclone warning from the perspective of community preparedness, and has been the subject of sustained attention in both the research and operational meteorological communities. The night shift at the operational center will begin in a few hours, and the meteorologists who will work through the night tracking the developing system will inherit the watch that the day shift started with the buoy anomaly identification this morning. The accumulated observations of the day, the satellite imagery and the scatterometer passes, and the reconnaissance aircraft data and the model output from the latest data assimilation cycle will form the context within which the night shift watches for the specific developments that will determine whether the watching becomes warning. The specific developments they are watching for are the standard markers of tropical cyclone genesis as seen in the real-time observational data. They are watching for the consolidation of the low-level circulation center, the tightening of the cyclonic wind field around a well-defined center that signals the transition from a disorganized disturbance to an organized tropical cyclone. They are watching for the development of a coherent warm core in the mid-troposphere, the thermal structure that distinguishes a tropical cyclone from the cold core extratropical cyclones, that also produce damaging winds. And they are watching for the establishment of sustained deep convection near the center, the convective organization that provides the thermodynamic engine for further intensification. If these developments occur, the operational protocols are clear. A formal advisory will be issued, a tropical cyclone formation alert, followed by the initial intensity and track forecast that will initiate the official watch and warning process for the affected coasts. The communities in the potential impact region will receive the specific alerts that will activate their preparedness protocols, and the meteorological communities watching will transition to the more structured and more publicly visible activity of managing the official advisories for a tropical cyclone that has announced its existence in the unmistakable way that only an organized tropical cyclone can. If these developments do not occur, if the system fails to consolidate or is disrupted by some change in the environmental conditions, the watching will eventually resolve in the other direction, with the development assessment being downgraded and the increased monitoring frequency being relaxed as the evidence supports a return to the background monitoring level. The communities that have been tracking the situation will be informed that the threat did not materialize, and the meteorological community will file the case in the record of disturbances that were monitored carefully and that did not develop, contributing to the statistical understanding of the development versus non-development problem that the Genesis research community continues to work on. The meteorologist who processes the night shift will not know when he begins his watch which of these two outcomes is waiting for him in the satellite data and the model output and the buoy observations. He will know that the situation is genuinely uncertain, that the evidence is genuinely ambiguous, and that the honest watching of a system that has not yet decided what it is going to be is the correct professional response to the current state of the evidence. He will drink his coffee and watch the satellite imagery update every 10 minutes and look at the microwave passes when they come in and wait for the reconnaissance aircraft data to land in the analysis system. And he will be ready in the specific way that experienced meteorologists are always ready when the watching might become warning to do what the data asks of him. The storm is still forming. The meteorologists are watching. The communities in the potential impact region are monitoring the official products and preparing to respond to whatever the watching finds. And somewhere in the western Pacific, in the warm, moist, convectively active atmosphere over an ocean that is warmer than it has been, the developing disturbance is doing what disturbances do when the conditions are favorable and the internal dynamics are working through their uncertain progression toward or away from the organized structure of a tropical cyclone. The watching continues because the outcome has not yet been determined. The determination, when it comes, will be visible first in the satellite data, and then in the official advisories, and then in the preparations of the communities that the advisories are written for. The meteorologists are watching because that is what the situation requires, and because the people whose safety depends on accurate and timely communication deserve the most careful and most sustained attention that the people who watch the atmosphere for a living can provide. That is what they are doing. That is what they will keep doing until the storm tells them what it is.